Record. Hello. So, we are going to do something fun and interesting today. As usual, anyone who's new here knows that just about everything I post is unscripted, unscheduled, organized chaos. So today, Darren is joining me in that. And, I'm so excited about what he's going to share. And yeah, just everyone knows none of this is high dopamine content. You grab your tea, hang out with us, and we'll see where it goes.
Yeah, cool. Well, thank you, Jana. I really appreciate you taking some interest in the stuff I've been working on.
I'm so excited.
Yeah. And I don't know, what do we want to start with? Because you and I have only known each other for a couple weeks. We've been sort of emailing back and forth, and
Yep,
we
yep.
only just started interacting virtually, like last week, I think. So it's new to both of us as well.
Yeah, yeah. So, okay, here's what I know, right? So, I know your
Yeah,
research paper is about divisibility patterns, right?
that
And
you got it. Perfect.
I love the word patterns. And I'll be honest, I don't know if I know that much beyond that. I know that,
Okay.
I've hung out a little bit in your tutor my math workshops and had some fun conversations with math, but I would really love to know more about your research paper.
Absolutely. And so a little bit about my backstory. I'll give you a short version. Didn't like math in high school, calculator dependent, lack of confidence, didn't think I was going to do anything math related. And then sort of got into it in college and started tutoring at a company. I worked for a woman named Lori. Lori taught me everything I know about teaching math. I was really grateful to work for her. And basically, because I went back and relearned like elementary school math in a way that made sense to me through working this job, like it really helped bolster my math skills. Went on to do a master's degree in math, had a career in data analytics. But the thing that I really love doing is teaching math. And that's sort of the current phase of life that I'm in. I wrapped up, I was doing a consulting business for data consulting, right? Because what do you do with a math degree? And I know you get this, like
Yeah.
go into data analytics, right? That's sort of the big thing. And
Yep.
so I was working this huge consulting project through my consulting business, got totally burned out, and had plans to like find a new client, all that stuff. And I thought, well, I don't really want to do that. What do I want to be doing? And this problem has been in my brain for a very long time. And like when I'm standing in line at the grocery store or sitting on a train, like this is what I'm thinking about. And I sort of just decided I just want to do this. How can I do this? Well, if I start teaching, like that's why I had the education business is like I can teach and that makes me better at what I want to focus on. But the last year or so, like I really wanted to write the research paper. That is something that I'd always wanted to do and never really had a chance to do. And as I started working on that, all of these sort of visual ideas started coming to me. And now I'm trying to draw it, I'm trying to write it, I'm trying to capture this one idea. And as you mentioned, it's about the divisibility patterns, and I'd love to tell you a little bit what about that means. But it all ties back to the divisibility tricks, which a lot of people in math sort of know, and there's tons of videos and other people posting content about
Mhm.
divisibility tricks. But do you know the divisibility tricks, Janet? Are you familiar at least with some of those?
There was a
Patterns?
moment
Yeah,
when, for about a week, I knew, and I forgot them.
yeah,
But I will say I do know there is one with the number nine. I definitely had one video where I played around with the number nine and it was so much fun, right? And it was just
yeah.
specifically the number nine because of our base 10 system, right? If it was like base 12, it would be 11 or something else, like, or who knows. But
Yeah, and we'll get into other bases because that ties in absolutely.
yeah. Well,
Yeah,
question though.
yeah.
I'm curious, do you remember, and no, if no, totally cool, but do you remember how you first got to this specific problem? Like
I
specific,
do, and yes,
okay,
let me give you a little bit more of the backstory. And so I was working for this company, and I'll say I was working for this woman, Lori, and again,
right.
amazing educator, amazing business owner. And what I really liked about working for that particular company, they had their own custom curriculum, but it was very number theory heavy. And again, like it gave me the skills, the number theory skills, the divisibility, how to break numbers down and understand fractions,
Yeah.
decimals, all those things. And so their content was very heavy in the divisibility tricks. It
Mm,
was something that we taught to the students, and I've taken that sort of with me and made it my own thing. Like the very first thing I teach any of my students is
Mm.
how to tell if a number can be divided by 2, 5, 10, 9, 6, 3, right? Just
Yeah.
going over these divisibility tricks. And so what it was, I like to joke that this is like the only time I've ever been paid to write a proof, is one day Lori got an email from the corporate office,
Yeah.
and basically they were trying to create some new curriculum, content, whatever. And the thing that the email said was, we would love it if somebody could prove the divisibility trick for 9. And so Lori came out and came to me and said, hey, like, it's not too busy right now. Why don't you go sit in a corner for an hour and see if you can prove this divisibility trick for 9, which was super cool. Like the fact that I got a chance to work on this for 1 hour and I was getting paid, 15 bucks an hour or whatever, which at the
Yeah.
time was fantastic money. And so like, and it turns out it's not that hard of a problem. It's not, and like, if you're interested in mathematics, and we can certainly take a look at it here, but it's not
Yeah.
that hard to figure out why that sum of the digits trick works for 9. And in fact, if you want, we can sort of start there, if I can start writing as we go through this, right? So the example that I
Yeah.
always like to start with is the number 3,456. And so for those who don't know, can this number be divided by 9? How do we check? Well, we take the sum of the digits, right? 3 plus 4 plus 5 plus 6. And then the easy way to add these, 3 and 6 is 9, 4 and 5 is 9, right? So 9 plus 9 equals 18. And so because 18 can be divided by 9, then the number 3,456 can be divided by 9. So again, the question that Lori asked is, well, how do you prove this trick? Like, why does this work? And so I proved it. Again, it's not that hard of a problem. And as you sort of said, immediately, as soon as you write the proof, you can see that there's a generalization. That the reason why the trick for 9 works is that 9 is 1 less than 10. 10 is our base number. And that actually there's a more general statement that in any base number system, the one less than, right, whatever your base minus 1 is, always gets this sum of digits trick, and so do all of its factors. And so 9 gets this trick, but also 3, right? A number can be divisible by 3 if the sum of the digits can be divided by 3. And it's normally, when I pose this question to math type people, they normally think that, well, if you can prove it for 3, then you can show that it works for 9. Well, it's actually the other way around. It works for 9, and then because 9 or 3 is a factor of 9, 3 sort of inherits that divisibility trick. And so that was sort of the start of it. And again, so at this point, I'm tutoring. I'm still in my undergrad, focused on that, went on to my master's, and honestly, didn't really think about that problem again for a very long time. And again, like, I took the divisibility tricks, and like that's the point that I always start with. So during the pandemic, I was again working from trying to build my own consulting company, but I realized that there would be a need for like virtual math education. And so I thought, I'll throw up a website and just get started. And I started tutoring my partner, Kayla, her nieces, or not nieces, cousins. Yeah, cousins. On, and basically I had free reign to teach them whatever I wanted. And so I started teaching them the divisibility tricks. And at some point, it sort of came back to my mind of like, well, that trick for 9 was kind of cool to prove. What was the divisibility trick for 7? And how do we prove that divisibility trick? And then from there, and that's sort of the process I'd love to take you through, is you start to ask questions and you start to look at, okay, well, why do these tricks work? What's the general pattern? And that's where we start getting very heavy theoretical. And then I sort of worked on all this stuff, got it to a certain point, and then connected it to another topic and realized that there was a connection between two things that I didn't realize were the same thing. And then it sort of exploded from there and kept growing. Does that make sense so far?
Totally. Yeah. I'm really curious to I don't know, to try some. But I was gonna ask also, how, like, so okay, when you were trying to prove, right, the divisibility trick for, let's start with number 9. What did you start playing around with in order to try and prove it? Where did your curiosity take you that led you?
And this is an interesting question, because if you really think about it, it's like, when we talk about the difference between math being invented or discovered, the way that we write this is a human invention. This is a notation. This is a system that humans came up with to represent, a value. But this idea of what prime factors a number has, or like how a number breaks down, that's a little bit more of an intrinsic, like, it's that's not,
it doesn't matter what
human-made.
shapes you assign to any of the numbers.
Right.
Given their place value, they'll always still have the same,
Exactly.
category.
it's prime factorization, all those things. Like they don't.
Yeah.
That's part of the universe for some
Emergent
reason, and that's
phenomenon.
that's exactly it, exactly right. And so one of the things we could ask, well, it's like, what does the digits of the number, like how does that connect to what its prime factors are? And that's sort of our starting point, is we want to somehow take this number. Oops, did my thing just flipped, didn't it?
Hey, when you said that,
Yeah.
that made something make sense, right?
Okay.
Because since we have 10 digits, that since we have 0 to 9 as our one digit numbers, in
Yeah.
every single place we have space for a one digit number, right?
That's interesting. Tell me more about that. I'm trying to figure out my thing, but keep going with that thought. I like
Oh,
it.
good. Yeah. So you do that. Because I'm thinking about how the reason it's whatchamacallit, literally 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whenever we're counting up the individual digits, we're counting up the individual places. Kind of how
Right.
like once upon a time in school, they were trying to teach us like the ones place, the tens place, the hundreds place, the thousands place. And like
Place value. Yeah.
yeah, and like you could look at it separate. Like you could look at it together, but you could look at each number broken down into that. Like you can look at 3,600, what did you write?
Hang on. Let me
3,656, right? And it could be 3,000 plus 400 plus 50 plus 6, right?
1,000 plus 400 plus 50 plus 6.
6,
Absolutely.
right? And so since for all of the numbers, I don't totally know where I'm going with this, but bear with me.
Keep going because you're on the right track. You're getting it. Keep
So,
going. Yeah.
we can always start with like it's easier to find divisibility, like to divide things when they have a bunch of zeros on the back, I think.
Yeah.
And so like for 3,000, if you were to take the 9, right? Let's see, you would have okay, I'm not totally sure where I'm going with it. I just feel like it has something to do with the fact that like we can separate it out into the one digit, and um since we only have 10 digits,
You're
I don't
on
know.
the right track. You've got some good ideas. I'm trying to get my thing to flip back around, and for some reason, it's not.
It
So
doesn't just leave it in the vertical one, and
let me
yeah,
adjust my stand. Pause for technical. I think we can still
pause
sort
for
of see.
technical support slash
Okay. How do we feel about that? Is that okay? Can we sort of see? I know it's maybe not great.
a little bit up, I would say.
Just go straight up on the stand. Somebody called me. I should have put do not disturb on.
All
Um,
good, all good.
okay, can we see that?
Yes.
Okay, so getting back to it. So what you
Yeah.
said here, Janet, is absolutely the correct approach. It's place value. And this is sort of where things will tie into different bases and all that stuff. But
Yeah.
already we've taken this number and we've expressed it in a different way. And what I like about this is that, we're trying to get to the sum of the digits. And so
Right.
now you've introduced sums into
Mm,
what was originally just a number. And that's exactly what we mean by place value, right? 3,456 is 3,450 and 6 added together. And so now from here, somehow we want to manipulate this so that we get an expression that gives us the sum of the digits of the number.
mm,
And
okay.
there's one more thing that we could do here to break this down even further, is when we
Okay.
think about 3,000, well, that is 3 times 1,000
Mm-hmm.
plus 4 times 100, right? 400s,
Yeah.
plus 5 times 10 plus
Plus 6.
6.
Yeah.
And so our digits, the 3, the 4, the 5, and the 6. And somehow we want to separate out the sum of just one of each of those numbers.
Hmm.
And so when we think about and it,
Okay.
when we think about what multiplication means, what do we mean by 3 times 1,000? What does that multiplication mean?
It means we either have three quantities of 1,000 or 1,000
Yeah,
quantities of three.
1,000 quantities of 3, right? 3 plus 3 plus 3 plus 3 plus 3 plus 3, a
Right.
thousand times. And the
Right.
idea is, let's take one of those threes and
Okay.
separate it out from the rest of the group. And so I've got 1,000 threes here. What
Yeah.
I'm going to do is I'm going to take one of them and put it aside, how many threes would I have left? If I have 1,000, I just take one away.
97.
If
No,
I have
are
a
we not
thousand,
subtract?
and yeah, just subtracting
Oh,
one though.
we're taking a whole one of the threes away. Okay, we
One
have
of the
two.
threes away, yeah.
Okay, we have two left of the threes left. So we got 2,000 threes.
Not 2,000 threes. That's if we were working in thousands. If I have
Okay,
a
hold on.
thousand
So
threes and
then
if I have 1,000 apples and I take away one apple, how many apples do I have left?
999.
999. So if I have 1,000 threes and I take away one three, that leaves me with
909. Oh,
9,099 threes.
9,000.
So
I was okay.
900. 900. Look at, we're all over the place.
Oh, okay. My
900
bad.
because it was three, it was a
Right, we're
thousand
taking
three.
away one three. We're not taking away three. Okay,
Yeah, we're getting there. It's still
we're
early. It's
getting
still
there.
morning.
Yes. See, even
Um,
people who graduated with math don't even always know how to do math. We're fine.
and the point of learning math is to make mistakes, right? We're here to make mistakes. That's how you get better at things, right?
Totally.
But
Totally.
so does this make sense now that we've taken a
Oh,
thousand threes and broken it
yes.
into, and let's do the same thing here, right? So I've got 100
Okay.
fours, and I can split out one of those fours, and how many would I have left? 99. And again, if I have 10 and I take one away, that would give me 5 9 times. And then the 6 is just 6. We're going to leave that one as it is.
So
But
that's
what do
why
we,
we have all those nines. We can divide by 9, take
you
out
got it.
all the nines, and that's why the only thing that's left is that sum, which will determine if that
Yeah,
last part is divisible by 9. Then the whole other thing is because the all the other parts are. We have the 999, we
you
have the
got it.
99, we have the 9.
Right. And so just to make that a little bit clearer, right, we're going to basically group together these three numbers, which have all the nines in it, and then the other
Yeah.
numbers, which is the sum of the digits, right? And so we've got
Mhm.
3 times 999 plus 4 times 99 plus 5 times 9, and then plus the 3 plus the 4 plus the 5 plus the 6. And so exactly like you said,
Got
the idea
it.
is that if this can be divided by 9, we know that each of these parts is already divisible by 9. And so when we add two things that are divisible by 9 together, or
Yeah.
many things that are divisible by 9, that means that the answer that we get at the end will also be divisible by 9. And so it's sort of like that distributive property factoring. But do you see that? Does that make sense?
It's nice. I do. It's all about like manipulating the format that we have the number in, playing around with different ways that we can write it.
Yeah. And so breaking it down, trying to understand that's what, and like, this is like elementary school math, really, of understanding what we mean by the number 3,456 is that we can break it down into its
Right.
place values. And then with a little bit of creativity and thought here, we can split it up even further. And then, so the idea is obviously this is just for one number, but if I have any number n, and this is where we're going to get slightly technical,
Yep.
but
Yep.
basically, if I have some number n, I can write that in terms of, we'll use even base 10, but I'm going to basically use the symbol like n sub I to represent
Okay.
the ith digit, right? So it's like if n has d digits, then it would
Yeah.
basically be like n, the last digit times 10 to the d power plus d minus 1 times 10 to the d minus 1 power, plus basically we can go all the way down to like n sub 2
Mm.
times, oops, that was supposed to be a 10 there, 10 squared plus n to the first times 10 plus n naught will represent sort of that last digit, the ones place.
This looks like a series and like the
And if we wanted to, we could express this as a finite sum, right? And we could say ni 10 to the I equals 0 to whatever the length of that number d, whatever that length is.
awesome.
And yeah, and so we can sort of do the exact same approach here, is from each of these terms, right? From each of these terms, we're going to take away the nth digit.
Yeah.
And so basically, like, we could write this as nd times, basically, we're doing this 10 to the d minus 1.
Yeah.
We take one of those factors away, and then we have to add it back in. And
Right.
algebraically, if you check, then this is for any term, this will
Yeah.
add back up. But we can see that we get this quantity, 10 to the d minus 1. And as we saw, that will always be a number that ends in nines.
Yeah.
And so one of the ways that we could sort of go from here is that we could think like, and actually instead of D, I'm going to just use I because we can think of it just like the general I term. But basically, instead of thinking about it in base 10, I could replace that with any base B, right? When you express a number in a different base, it's just
Mm.
like you're changing out what
Mhm.
that power is. And it all, again, it has the same properties. It just is expressed using different
Yeah.
coefficients,
Yeah.
digits. And
All the
so the idea
computer
is,
science people have such great experience with different bases.
yes, and that's why so many of the people that come to like the proof session that I do for this are actually sort of in computer science because they definitely resonate with this problem quite well.
Yeah.
And so, and the idea is like from here, if basically what we want to do is we want to take away one ni and add another, right? So
Yeah.
we're keeping things in balance, which then leaves us with ni b to the I minus 1 plus ni.
Mhm.
And again, we're getting very technical here, and I'm sort of want to leave some of the details here for the viewer to figure out on their own. But this 10 to the or b to the I minus 1, if we think of that as a polynomial that we might see in algebra 2 or like a college algebra,
Mhm.
that can always be divided by b minus 1 times,
Yeah.
there's other factor that goes there, but it's always divisible by b minus 1. And so this is sort of why, and again, there's a lot more to say here, but you can take any base and the b minus 1 value always gets this sum of the digits trick. Does that make
Wow.
sense so far?
Yes, totally. I'm following. I
Yeah.
love it.
Perfect. And so this is how I got into it. And again, like I proved it. I saw the generalization to the other base. I was like, oh, that's so cool. I was so excited to tell everyone about it. And then kind of just forgot about it for the
Right.
longest time until
And
I
now you're
revisited it. Yeah.
now you're like other numbers. What about the other numbers?
So, and right. And so that's the trick for 9. We have the trick
Yeah.
for 3, which also works the same way, right? The sum of the digits. So like I can tell that this number is
Right.
divisible by 3. And then
Right.
the sort of the easy ones that most people know without even having to call them divisibility tricks is how do you tell if a number can be divided by 2?
Right. If it
If
ends
it,
in 0, 2, 4, 6, or 8.
yep. So for 2, I only have to check that last digit. I don't
Right.
have to look at any of the other stuff. I know that this number is divisible by 2. But if you
Right.
think about it, that same trick works for 5. Because if
Right.
you want to tell can a number be divisible by 5 or is a multiple of 5, well, that last
Right.
digit will either be a 0 or a 5. And the same trick
That,
works for 10. Go ahead, take a second.
yeah, just I'm wondering, does that have to do with the placement of those numbers within the base? Like where they like if they're halfway through versus like because like you know how 9 we have one back from the last number
Yes.
and 2 we have one forward from or I don't know if we would call 2 1 or 2 forward from the first number depending on if we're starting at 0 or 1 or just 0 exists for all of them and we're just you know
Yeah. You're asking some great questions here, Janet. And this is exactly how we start to think about things like why is it that one number has one trick and one number has another trick? Well, what do
yeah
2, 5, and 10 have in common? Like,
2 and
because the
5 are
point was is that
factors of 10
of
right
10 is
yeah 2 times
what
5 right it's fact
what is
those are
special
fact
about 10 though?
oh the first number that is the two-digit number? It's a
Which
combination
means,
of
yeah,
one
that is very true. It's the first digit that is a 2-digit number because it's our
base.
base,
Yeah.
right? And let me see. Do I have here are I'm gonna start pulling out some of my stuff. So here
Yeah.
is for the base, and somewhere I have a really nice picture. I like to draw. I don't know if you can see that the 10 with a little crown on it
Yeah.
sort of indicates that it's the base number. And so dividing by the base number is very easy. Dividing by 10, multiplying by 10, working with 10. If we can
Yeah.
work with 10, that's great because we can look at that last digit and say, how do I tell if a number is divisible by 10?
Right.
Well, if it ends in a 0.
Right.
And actually, this is not quite the one I wanted to pull out, but, and we can even sort of take that further and say, well, how do you tell if a number can be divided by 100, which is 10 times 10, right? 10 squared. Well, multiples of 100 end in 2 zeros. And so there's something about all of these numbers that their trick seems like there's a connection, and there is a connection. We'll get to that in a second. But now let's try a number that's a little bit crazier. just to see what other variety we might have. And 7 is sort of our example that
And it's the hardest one.
it breaks everything, but it also reveals the deeper theory of what's going on. So the number that I like to
Okay.
start with 7 is 343.
Okay.
And the question is, can 7 go into 343 evenly without actually having to do the division? Right? We just want to check to see
Right.
yes or no, is it a whole number answer or will there be a remainder? And the
Right.
way that this trick works is you remove the last digit of the number. So you take off the 3 and you
Okay.
double it.
Okay.
Okay, so 3 times 2 is 6. And then we subtract the 6
Okay.
from the remaining digits. So we take 3 times 2 is 6, whatever that last digit is times
Yeah.
2, subtract from the remaining digits. What is 34 minus 6? Take away
28.
28. You got it. I was going to say take away the 4 and then take away 2 more. That gives us 28.
Yep.
And what do we notice about 28?
It is a multiple of 7. It is 4 times.
Is 4 times 7. And so because 7 goes into 28,
Yeah.
7 goes into 343 without a remainder. Doesn't tell me what the answer is going to be, just that it goes in there an even
Right.
number of times.
Right. Question. Is there
Go
like
ahead.
there's got to be like a limited number of multiples of 7 that it can go up by before it starts repeating, right? Because like once you get bigger numbers, then you just have to do it over and over until you get to 2 digits or
You mean like applying the trick?
yeah, because like what if you have like a
Yeah. Go ahead. Ask the question.
or just like 4 digit number, or like or if you get
You're
something higher than 28, if you get like 280.
right. If we get some number and we don't know for sure if it's a multiple of 7, well, there's two options. You can reapply the same trick,
Right.
or the one of the questions that we're going to ask in a little bit is there a more general version of this trick?
Mm,
So the first question
okay.
is, well, let's just start here. Why
Yeah.
does this work? What is it about taking off the last digit? Why doubling it? Why subtracting? Why does this tell
Yeah.
me if it can be divisible by 7? And actually, this is one version of the trick. My good buddy Mark actually uses a different version of the trick where you take your number, 343, and instead of taking off the last digit and doubling it, take off the last digit and multiply by 5.
Okay.
And we get 15. And now instead of subtracting the 15, we're going to add the 15. And so 34 plus 4 or 34 plus 15, that's 49, which is 7 times 7. And so
Yep.
again, we get a multiple of 7. And so we see that yes, this 49 is divisible by 7, therefore the number 343. And so here's two tricks. Now we have two different
Right.
tricks. And again, it's like, why multiplying by 2? Why multiplying by 5? Why adding? Why subtracting? Does this have anything to do with 2 and
Right.
5 that we saw earlier with the bases? We start asking questions. And so going back to sort of the story, so now I've got my own math tutoring business that I'm trying to grow. And like, this is the problem that is now starting to creep into my mind and dominate my thoughts. So I'm trying to build a data consulting business. And at the same time, it's like, I actually want to just be thinking about this. And if we look at the trick for 13 and sort of compare, it's
Okay.
similar. For the trick for 13, you take off the last digit, you multiply by 4, and then you add. And it's like,
Okay.
okay, so there's a similarity between the trick for 7, the trick for 3. We've got the sum of the digits trick for 9. We've got the trick for 11, actually, is what we call the alternating sum of digits. And I know I'm jumping around here
Okay.
a little bit, but the trick
All
for
good. All
11
good.
looks like, actually, hang on, bear with me for 1 second,
I
because I
will say
have,
though, if
yeah,
they
go
were
ahead.
showing me this in school for the first time, I would be like, how? And like, does it actually work? I would try it like 1,000 times. And then I would be like,
Yeah.
okay, then I believe you.
And you can play around with, you can try and figure it out just by trial and error, but then as you start to ask these questions of why does it work, you can get into the advanced math and actually try to prove some of this stuff. And like, it's
Right.
frustrating to me because I'm working with a middle schooler right now, and the stuff that he's learning is just boring. And it's like there's no question there. It's just type it into the calculator, and that's your whole process. And it's like at least with this, we're asking questions. And
Right.
I wanted to show you this one real quick. Here's some more examples of divisibility trick for 7. So like if I have
Yeah.
a 4-digit number, like you said, we still take off that last digit and subtract. So 153 minus 6 is 147, which in this
Right.
case, we can actually see 14 is divisible by 7 and 7 is divisible by 7. So like it's
Right.
not too hard to see that that goes in there 21 times.
Right.
But
Okay.
sometimes you get like 91. And if you're not entirely sure, so like here was 931, take off the
Yeah.
last digit, double, subtract, we get 91.
Yeah.
If I don't know, does 91, can that be divided by 7? We'll take that off, multiply by 2 again. So take off the
Do it
1,
again.
multiply, do it again. You get 7. The 7
Got
tells
it.
me that 91 is divisible by 7, which tells me that 931 is. So you can keep
Got it.
chaining it. Another trick, and I'm sort of just going through the tricks real quick just to show that there's a variety here. The trick
Yeah.
for 11, how do you tell if a number can be divided by 11? And so I'm just going to redo this example here real quick. If I have the number 165 and I
Yeah.
want to know, can this be divided by 11? Instead of the sum of digits trick, we do what I call the alternating sum. And so starting on the left, you take this one as a plus, and then every other digit is a plus. And then
Right.
all the digits that you skip, you assign a minus.
Okay.
So plus minus, you basically start on the left, go plus minus, all the way down for however many digits you have. And then what you do is you add together all the plus numbers. So 1 and
Okay.
5 is 6. You add
Right.
together all the minus numbers, which in this case is just 6. And then you subtract them. And 6
Yeah.
minus 6 is 0. And because 11 divides 0, 11 divides 165. And it's like, okay,
Wait,
so
didn't
11,
11 divide 0?
yeah, any number can be divided by 0, right?
Right.
You
Right.
can't
Wait.
divide by 0. You can't take something
Right.
divided by 0, but 0 divided by something is always
Right.
0. If I have 0 cookies
Right.
and I share it with 11 children, how many cookies
Right.
does each child get? Well, they each get 0. So it works out,
0.
right? And
Yeah.
so this trick for 11, right? You take the alternating sum, you add up, you subtract, and then typically you'll either get a 0, a positive 11, or a negative 11. And that sort of just tells you.
Got it.
Yeah. But so the question that we can start asking is, well, do all numbers have a divisibility trick?
Okay.
Which one? Well, that's a very reasonable question. It turns out, yes, we can
Mm,
define a trick for any number that you can think of has one of these tricks. Then we start
awesome.
to ask, well, what is like the pattern here? How do I determine if I give you
Mm,
some random number? How do I determine what its divisibility trick is going to be?
mm,
And we can then start to look at, like we talked about a second ago, and so I sort of have a list here. I like to just go from 2 to 13 and start thinking about what the
yeah.
different patterns are. And I haven't written them all down here, but like for 2, and I don't know if you can see that or not, but we said for 2, you look at the last digit of the
Yeah.
number. For 5, you look at the last digit of the number. For 10, you look at the last digit of the number. How do you
Yeah.
tell if a number can be divided by 4? Do you know this one?
We look at the last two digits, right? So it's like 2, but we just add another digit.
Exactly. And so the trick for 4 is look at the last 2 digits. What's the trick for 8? Do you know?
Would it be the last 3 digits? It's
You
like
look at
2 to the third power.
you look at the last 3 digits because it's 2 to the third power. And so the trick for 2, 4, 8, 5, 25, 125, 10, 100, 1000, all the powers of the base, all the powers of the factors of your base and all of their multiples, get this nice trick where you can just look at the last few many digits, and so it feels like those are all the same, right? In some way.
They have like
Yeah,
a common like root in a way.
exactly. And so we can make that a little bit more formal in a second. But as
Okay.
we look at numbers like 9, well, 9 is 1 less than 10, so it gets that sum of the digits trick. And
Yeah.
3 gets that same trick because it's a factor of 9. And it
Okay.
turns out 11 gets this weird alternating sum of digits trick because it's the
Right.
base plus 1. These
Um,
two get like special powers because of where their position is next to our base number. The rest of them get their tricks because of their multiplicative relation to the base. And what we mean by that is, right, 2 is a factor of 10, right? They're a common factor, but something like 7 is what we call coprime to the base. It has no common factors. It's sort of like just sticking out there all by itself. And so that's why 10, 13 get the weird tricks. A number like 6, what trick does 6 get? Well, the way to check for 6 is you check, does 2 go in and does 3 go in? So is it even? And what are the sum of the digits? And so if 2 goes in, 3 goes in, then 6 goes in. And so we start to look at all of these different pieces. And it's like, well, what's the general pattern here? What are your thoughts on this so far, Jenna? I know I said a lot just then.
No, no, it's
There's a lot
great,
to
great.
unpack, but
I am totally following completely.
perfect, perfect, perfect. And so as we start to look at like what are these patterns, and so actually, where do we want to go from here?
Where
The
do we
I
want to go?
and so that's
Anywhere,
part of
anywhere you want to go. We can we
yeah. And that's part of what I'm trying to like show with all of these crazy drawings is when are they the same? When are they different, right? So here's divisibility trick for 10, 2, and 5. We already said it's
Yeah,
last digit, last digit, last digit. Then as you start looking at powers of 10, it's
yeah,
based on like 100 is the last two digits, which is the
right.
same for 4 because 4 is a factor of 100, and the same for 25 because 25.
Right.
But getting back to like the trick for 9, the trick for 11, so we sort of proved those. And I guess
Yeah,
going back to sort of the story is now where we're at in sort of where I was at is we have this trick for 7.
yeah,
We know what it is. How do we prove that this trick
right.
works? And again, we're sort of asking the question, well, why does it work? What is it that you remove? Like, it's so weird. Remove the last digit, multiply it by something, add it or subtract it. And then if that number is a multiple, like,
Well, clearly
yeah,
whoever figured it out knew the pattern, right? Because they might just tell us what the trick is, but you can't figure out what the trick is without playing around with the patterns, right?
exactly.
I would
And
I
so
would hope
go
for
ahead.
trying out the same thing at first that we did with the number nine and breaking it up into like
Yeah.
what other ways can we look at this number?
Do you want to do it? Do you want to do it
Yeah,
real
I
quick?
want to do it. I want to
And
do it.
so we are going to, first of all, I'm going to throw sort of a definition out there. Um,
Yeah.
our divisibility coefficient, I use the letter A. In this
Yeah.
case, we're looking at -2. And what do I mean by that? The -2 is we multiplied by 2 and then we
Mhm.
subtracted. Whereas here we would multiply by 5 and we add, so we would call that a +5. We're going to think of this as multiplying 3 by -2 and then combining. And so we'll put a
Got
little
it.
bit more substance behind that in a second. The point is, though, we know that 2 is the trick. And so, first of
Right.
all, let's get really formal. What's the formal proof? What's the statement that we're trying to prove here? If we were to actually write it as an if then or an if and only if statement.
Right. Right. So if a if there exists a number, right? First,
Sure.
we must always, as mathematicians, create the objects that we are working with. We must give
Absolutely.
them existence. Um,
Or prove their
the,
existence, right? Yep.
yeah,
Go
exactly.
ahead.
So if there exists a number that, like, are we working just with whole numbers, integers right now?
We are just working with the naturals. Yep.
Okay, so
And let's take a step
yeah,
back for a second because I get that you're trying to bring this in, but just thinking of like what does the divisibility trick for 7 tell us? We take off that last digit, we
yeah,
multiply, we know the number, and so let's start with knowing the number. So we could say, given
right,
a number, a natural number n, we'll do n in purple,
right.
um,
The
and some.
last digit times two subtracted from the
I'm going
rest
to say, yep, you got it. And
of
somehow we
the
have to sort of formalize that, right? It's complicated, but
right
a natural number n is divisible
by
by
seven
7
if
if, and it turns out we're actually going to get and only if, although we can talk about that like
don't
maybe step up, but a number n is divisible by 7 if, and then we have to somehow say, and actually it's kind of hard to think about it and write it out. And so we know that we're going to take off the last digit, multiply by -2, and then subtract the remaining digits. And so maybe what would help is starting with, before we finalize this, and again, I know we're jumping around, but we're trying to figure it out as we go. Let's think about n.
yeah, and like how do we describe, that last digit and those were before ones
Yes.
without specifying what they are, right?
How do we specify the digits of n? And what we're going to do, and this is actually the way that, and I'll show you my book in a little bit. I've got a number theory book that I carry around with me. And the way that the author of that book sort of denotes it is he sort of goes, well, we have, like nd minus 1, dot, 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 all the way down to n2, n1, n0. And so what we're saying here is that n0, this is the last digit. And the zero is not arbitrary because the idea is that as we break this into sort of like a power of 10 or break it down into its place value like we did for the last one, the index on this variable represents the power of the base, the power of 10, that digit is being multiplied by. So it's like n2 times d, or I did it again, 10 squared plus n1 times 10 plus n naught is like 10 to the 0 power.
Right. The thing I'm thinking about is
Yeah.
almost like this Excel formula where like if you have like a full number, you can divide by 10, but then you just drop whatever the decimal point is, so you don't care what the decimal point is, and that'll give us the rest of the
Yeah. And so you could cut it off and round down, basically, would
yeah,
be like the formula there. And so what we're going to do is we're going to isolate
the
n0.
last. Yeah.
And it's funny because what you said, because you divided by 10 and then took off the digit. We're actually going to do it the other way around. We're going to take off that digit. And so again, like if we think of the number 343,
Yeah.
this as a concrete example,
Yeah.
we know that our last digit n naught is going to be 3. Well, our remaining digits, if we just sort of take the 3 to one side, we should really be talking about the number 34 or 340.
40.
But
Right.
we don't want to talk about the number 340. We're going to talk about the number 34 because that's the remaining digit. So somehow we have to write an expression that isn't just, we could just say,
got it. So minus n naught divide by 10.
what we're going to do is actually we're going to yes. And so what we're going to do.
I'm pausing.
Let's look at it like this. And again, I'm going to try and do this as sort of a finite sum. And again, if you're interested in the math of it, play around with this. I'm not going to do every single detail here. But basically what we're doing is we're taking our number n and we're writing it from like I equals 0 of ni times 10 to the I. Right? This is the ith digit times the power of 10. And what we're going to do is we're just going to rearrange, or we're just going to take one of those digits off and say that this is I to the first ni to the I plus n naught. We're just taking that last digit and moving it off to the side there. And if you, again, check your sum rules, this is maybe like pre-calc level math or above. But you should see that these two things are equal. Notice now that everything here, it's like 10 to the d minus 1, all the way down to 10 squared times 10. All of these numbers have a common factor of 10. And so this is where that dividing by 10 comes in. We're not actually, instead of dividing, we're just going to factor it out, which in a way is kind of the same thing. And so we could say that from this expression here, this is 10 times I equals 1 of ni times 10 to the I minus 1 plus n naught.
Okay.
And so this represents the last digit.
Right.
This quantity here, ignoring the 10, right? This represents the remaining digits.
Yeah.
Does that kind of make sense? And again, I know I went through that very quickly. There's a lot of complicated stuff happening here, but now we've written n as its last digit plus the remaining digits times 10. And so when we go back up here and say, well, a number n is divisible by 7 if and only if the remaining digits, which is the quantity, if and only if the sum from I equals 1 of n, I 10 to the I minus 1 plus the last digit n naught, which we're saying n naught, the last digit times our divisibility coefficient, our number, whatever number that we're looking at, times a. And so that's very complicated. But from here, you can actually prove that this works. I feel like we may have lost the plot slightly. But again, this is sort of just a very...
would you prove it with like I remember I had a proofs class And we
Yeah.
talked about different types of proofs, right? You could prove by contradiction, you can prove by, I feel like this one would be kind of like, I see the eyes, and every time I see the eyes, I feel like the proof has to do with like, okay, if it works for I, and then if it works, you can prove it works for I plus one, then you prove that it works for all of them.
And you're thinking, right, induction, right? And
Yeah,
basically,
yeah,
that's kind of
yeah.
what we did in that trick for 9 is we can look at just one term and then
Yeah,
argue that it works for the rest of the terms. And yeah, so again, let's sort of
yeah.
put a pin in it here and say, see if you can sort of figure it out from here, any viewers.
Yeah,
With
any
that,
math people, try it out.
the
Or not
next
math
question
people.
is, well, where does A come from?
Yeah,
What is this number 2? And I guess really the point that I was trying to show is that
yeah.
the reason why it's a 2 is because when you're constructing your divisibility trick for a number like 7, we're looking for a multiple of 7
Mhm.
that is either one more or one less than a multiple of your base, which is a lot. So the idea is we're trying to find a multiple of 7 that
Okay,
basically ends in a 1 or a 9.
okay.
So what's the first multiple of 7 that comes to mind as we think about ending in a 1 or a 9?
21.
21. So think about the number 21 is equal to 2 times 10 plus 1, right? Here's our base.
Uh-huh. Yeah.
One more than, and so again, this is like 7 times 3 is 21. And it turns out the 2, this 2 here, comes from this 2 here. Because it's 21, it's 2 times 10. And then because this is a plus, we take the opposite and we make it minus.
Oh,
And the reason the other trick works for 5 is that 7 times 7 is 49, which is
right,
equal to 50 minus 1. And
right.
50 is a
Five
multiple of
times 10.
5 times 10 minus 1. And so the other divisibility coefficient we can use is 5. And because it's a minus 1 here, the other one would be adding. And that's what we saw.
Oh, and I get why we're using the one and the nine because that's because we're in this base 10, right? So we're using the one that's one more than the first or one less than the
Exactly. And the idea is that, again, 7 has nothing common with 10. And so we're
right,
guaranteed that there will be a number that ends in a
right.
1 or a 9 for 7 in base 10. And again, we can generalize this to any
Um,
base, and we get a really nice way of calculating. And I'm just going to write it really big here. Basically, in any base, if you want to find the divisibility coefficient for some number k, then you have to find a multiple of k. And so basically, we'll just use any letter m, any multiple of
yeah.
your divisor that is equal to a multiple of your base plus or minus 1. And using this, you can prove a very general divisibility trick in any base for any number that is relatively prime to the base. So this works for 13. If you go to base 12, it still works for 7 and 13. And again, we're skipping a lot of detail here, but I want to sort of rein us back in because I got a lot more to
Yeah.
say. And I want to make sure we're... So again, this is left as an exercise to the reader because we can prove this trick. We can also go back and talk about the trick for 2, 5, and 10, and we can set up a trick there and try to prove that. And again, I talk about this on my Friday sessions if anyone wants to get into the nitty-gritty details of all of this.
I can definitely leave all the links in the description of this video.
Yeah.
Just send them over. Also, I gotta go in a minute to another meeting, but
Yes. Well, let me sort of
yes,
bring it all together, right? Because one of the
yes.
questions we're asking is like, well, what is the connection between all these things? And it turns out you can group all of these numbers into 3 groups based
Okay.
on whether they have common factors with the base and only common factors with the base, no common factors with the base, or a mix of both. And
Ah,
it turns out when we're talking about multiplicative stuff, there's only 3 divisibility tricks. There's only 3. You can prove all divisibility tricks for all numbers in 3 statements.
okay.
And the reason why it's interesting and where maybe we could go another time is
Would love
that
to, for sure.
those 3 groupings that you get are the same 3 patterns that you see when you convert a fraction to a decimal. Because there are 4 types of decimals. There are the irrational ones. We're not talking about those ones right now. There are decimals that terminate. There are decimals that repeat forever, like
Repeat.
1/3 is
Yeah.
0.3333. 3. And there are ones that have a repeating and non-repeating components, like 1, 6,
Right.
0.1, 6, 6, 6, 6, 6, 6, 6. And so
Right.
it turns out which divisibility trick you get is the same pattern as to what the one over that number, what its decimal pattern is. And there's actually a
Huh.
much bigger idea that we can connect these two and build a more general divisibility trick using this connection. And so there's a lot more to the story, but that's sort of the idea where we're going, is that the decimal pattern and the divisibility trick are actually the exact same thing. And one is
Wow.
with remainder, one is division without. And so it's taken me a few years to get to this point, but that's sort of where we're going with it, is we're taking these divisibility tricks and connecting it to something that, as far as I know, I've not found anyone else who has connected it to this idea. And so
Wow.
that will be sort of where we would go from here. What do you think?
Let's do a part two. Would you
I love
like
it.
to?
I would
I
absolutely
I
like
love
to.
it. I love where we've gotten to. It's like welding together different
Yeah.
different concepts.
And at the same time, it's going to blow up and get messy and get crazy. But there we go. That's sort of the intro to what I call divisibility patterns, is whether it has remainder or not. There's 3 things that we can see that show up all over the place. And so I'll shut up now. But again, this is sort of when I'm standing in line for the grocery store, this is what I'm thinking about. These are the things that I see in my mind of like, and I'll show you, and then we can wrap it up real quick. Just one last thing, like the final answer of it all is
Yeah.
this picture here, which I have written somewhere better, but I can't find right now.
I do
Is
remember seeing that page that you had opened to. Yeah.
this one, the one
Yeah.
that we started with? This is the general theory behind how fractions convert to decimals and what the divisibility patterns are. And there's a lot to prove here, but
I will admit, just looking at it, I couldn't explain to you what you're probably going to explain
yep.
about how it works, which is great because that means that there's something I don't know. That means there's something left to learn.
Yeah, and it turns out this is just long division. And so I know we hate long division, but it ends up being the answer to everything in the end. So yeah, I guess
That's
let us know part
hilarious.
2.
Yep.
Cool. All right. Well, thank you, Janet. I really appreciate you taking time to listen to me ramble on about my
Thank you,
crazy
Darren. That was
ideas.
so fun. I learned, I definitely didn't even know that. Like I don't remember the last time I actually used or worked on divisibility tricks, and I completely forgot that we can even rewrite numbers in different ways. Like once we got to
Yeah,
college, we never even did that. We didn't, I don't,
right.
you know?
But it's a good gateway into algebra concepts, and it's a good gateway into number theory concepts. And so that's why I love it, is that it's accessible at all levels, and there's some really fun problems in there. If you're looking for a proof or a challenge, give
Yeah.
these things a go. See if you can solve them, because they're a lot of fun.
Yeah. So anyway, for everyone
Yeah.
watching, right? If you guys want to give it a go, give it a go and let us know in the comments if you figure anything out. I'll leave all the links to Darren's website, to what he's working on. I'm so excited for your research paper, and
Yeah.
we will definitely do a part 2 because I want to know more. So
There you go. Awesome. Thank you, Janet.
excited for that. Thank you.